feel like I have dishonored the title boss fight in some sense by this assignment, but you'll forgive me for not living up to the hype. But anyway, Father, we thank you for this day again. I thank you for this class, and just ask that you'd bless our work today, Lord. In your name I pray, Lord Jesus. Amen. Okay, so today I want to talk to you guys about partial differential equations and like how do we solve those. And so a partial differential equation is an equation which involves more than one independent variable. All right. So there's tons and tons of different partial differential equations. Right. There's they're ubiquitous. They're like everywhere in science and engineering. For example, if you have maybe you recognize this, the divergence of the electric field is the charge density divided by epsilon naught. Or the divergence of the magnetic field is 0, or the curl of the electric field is minus the time rate of change of the magnetic field, or the curl of the magnetic field is mu naught times the current density plus epsilon naught partial E partial T, right? Do you guys know the name of these ones? What are these? Any electrical engineers in here? Are there no electrical engineers in here?
I'm an electrical engineer, but I can't remember. I feel like I should.
Oh no. But you didn't have the fields and waves course yet, no?
No.
Okay, so it's defensible. But these are Maxwell's equations. So basically these formulate the basis for electricity and magnetism. Solving this set of coupled partial differential equations constitutes the study of electricity and magnetism. So, and these are all partial differential equations, right? Because you guys remember the divergence and the curl are both in terms of like partial derivatives, right? X, Y, Z derivatives and so forth. And this also has time derivatives. So this is an example of a set of partial differential equations, which is of course very interesting. Now, you also may remember, or maybe not, from your Physics 232 course, if you've had it, I don't know if you have, that the electric field is minus the gradient of the voltage function, right? And so if the charge density rho, which is dq dv, all right, charge density, is equal to 0, then Gauss's law becomes the divergence of the electric field is equal to 0, but that becomes the divergence of minus the gradient of the voltage function is equal to 0, which gives us that what's called nabla squared v is equal to 0. So this is called Laplace's equation. Laplace's equation. And this is something we'll learn to solve in here. Right. Now we're probably just going to solve Laplace's equation probably in the plane, maybe in 3 dimensions, something like that, okay? So this is Laplace's equation. And we'll see how we can solve that. Now another example of a partial differential equation that we're also going to solve is something like this. Partial u partial t is equal to k times nabla squared u. So this right here is the heat equation. This describes how heat flows through some. Now this nabla squared could be, you could interpret it in 3 dimensions or in 2 dimensions, right? So like in the plane, well, okay, so here's one-dimensional heat equation. Partial u, this is the one we'll actually spend the most time on. Partial u partial t is, k times uxx. So like the one-dimensional, this is called the Laplacian, by the way. This is Laplacian. Laplacian of u. So the Laplacian in one dimension is just the second derivative with respect to position, right? So this is the one-dimensional heat equation. What would the heat equation look like in 2 dimensions? By the way, u here is the temperature function. So u would be like the temperature, right? So in 2 dimensions, the heat equation would look like ut is what? Like k in the plane uxx plus uyy, right? That would be the 2-dimensional. And I think you can see where I'm going here. If I were to do 3, we'd do what?
K times uxx plus uyy plus uzz.
Plus uzz, that's right. That would be the 3-dimensional heat equation. And we could solve all of those with the technique I'm going to show you guys. All right. Today we'll probably just solve the 1-dimensional heat equation. All right. If we do that much, we'll see. So these are important examples of PDEs. Another example of PDE is this partial squared y partial, I don't know if I can remember it, I think x squared is equal to 1 over v squared partial squared y partial t squared. I think dimensionally that's reasonable. Here v is like a velocity. So if you think about the units here, this has got like a meters squared over second squared, and I'm multiplying it by like a second squared, so you're left with a meter squared division both sides. So I think by dimensional analysis I remembered it right. But this right here is this describes like waves on a string, for example. It's the wave equation. All right. Fun fact, if you take Maxwell's equations and you study the vector identity, that the curl of a vector is minus the Laplacian, minus the gradient of the divergence of A minus the Laplacian squared of A, if I remember right. If you study that vector identity paired with Maxwell's equations, what you'll get in the absence of this right here, given that your current density is equal to 0 and your charge density is equal to 0, you can show that partial squared E partial t squared, oh my bad, no, that's fine. So yeah, 1 over c squared, that is equal to like nabla squared E, and 1 over c squared partial squared v partial t squared is equal to nabla squared v. So these two wave equations follow from Maxwell's equations if you sort through that vector identity at the top of the board. And so here c is defined to be 1 over the square root of mu naught epsilon naught. So like this little vector identity paired with Maxwell's equations suggests that in fact the electric and magnetic fields solve a wave equation. And the speed of that wave is the speed of light. So like the constant speed of light is implied by Maxwell's equations is a fun little like exercise. Well, it's calculus 3 though, it's not this course. So, all right, anyway. So there you go. There is a lightning tour of some important partial differential equations. We'd like to learn how to solve these in as much as we can. And so for this course, I'm just going to teach you how to solve Laplace's equation, the heat equation, and the wave equation. That's all we're after, all right? And pretty much in the most vanilla of circumstances, all right? So mostly one-dimensional. Listen, notice that these are not disconnected pursuits, right? You notice that if you solve Laplace's equation, you're solving the time-independent, you're solving the steady-state solution of a heat equation. See that? If you have partial u partial t is 0, this reduces to Laplace's equation. So the story of these equations is not disconnected either. You know, there's interplay between these different stories. All right, and if you want to see more about how to solve the wave equations for the electric and magnetic field, well, maybe come take Physics 331. I've spent a couple weeks in there solving those. Anyway, so here's the deal. We need to talk about boundary value problems. BVPs. And just to give you a brief motivation for why that is, take the heat equation, for instance. If we have like a, metal, here, I don't know, a stick, okay, some material, and here's x equals to 0, here's x equals to L, and, with temperature U of x comma t, right? We want to study the temperature along the stick in the x direction, right? And we can study different boundary conditions, right? Like, for instance, we could fix the temperatures, we could like put ice bath both ends, And so we'll work with Celsius. So we're talking about like U of 0 comma t is equal to 0, and U of L comma t is equal to 0 for all time, right? We could say for all time positive if you like. We usually study positive time solutions in here. Just like the story with Laplace, like the Laplace transforms? What were they called? Were they Laplace transforms? Goodness, I've forgotten the name of the transform. That's not a good sign. That's a different use of the word Laplace, isn't it? That feels really bad to forget the name of a technique in the course you're teaching. Whoa, it's very bad. Now, on the other hand, if you want to say that the ends are insulated, right, then I think that amounts to insulated ends. You could do partial u, partial x at 0 is 0, and partial u, partial x at L is equal to 0. All right. So those are, those are two different boundary conditions you could study. All right. And of course, you could mix and match, right? You could put one end at ice bath, the other end insulated, or vice versa, right? So there's 4 elementary boundary conditions to consider. All right. So here's the technique that we use to solve PDEs is separation of variables. All right, so I need to talk about that a bit here in order to make sense of why I'm talking about boundary value problems. So the separation of variables technique, it starts with a rather bold suggestion. It says to solve partial u partial t is equal to k times partial squared u partial x squared, assume that your function, your solution, u of xt, can be written as x of x times t of t. This is the separation of variables guess. All right. I believe we have Fourier to thank for this. This is Fourier's idea. At least it is until somebody can prove to me otherwise. So, but none of you are math historians, so I'm probably safe. You're like, we have Google. Fine. Prove me wrong. But look, so here's the thing. This gives us, well, if you look at the boundary conditions, right? If this is what our solution is going to look like, let's see what it does, what these boundary conditions translate into. So we've got like, x of 0, t of t equals to 0, and x of L times t of t is equal to 0. And this one becomes, x prime of 0 times t of t is equal to 0. And x prime of L times t of t equals to 0, right? And look, these hold for all time. So what does that mean for us? Well, that means that in order for our product solution to fit the boundary conditions, it must be the case that the x part of the solution fits the boundary conditions. See, so like these ones up here tell me that I must have x of 0 is 0 and x prime of, x of L is equal to 0. So this is like, the boundary conditions for x, all right? And likewise, these ones, not surprisingly, suggest that we would need boundary conditions like x prime of 0 equals to 0 and x prime of L equals to 0. So these would be my boundary conditions for the spatial part of the solution. All right? Do you see why those have to hold? Because the time solution, if the time solution is 0, well then our solution's just 0. That's not interesting. We're looking for non-zero solutions, right? So we must force the spatial part of the product solution to solve those, right? Okay, so then what? Well, so that's the boundary conditions we're going to have to solve for x. But what else can you say about x? Well, notice that we've got this differential equation we're trying to solve, right? So what happens when we plug the product solution into that differential equation? Notice that, like, u sub t is just equal to big X times t prime, and u sub xx is just equal to x prime prime times t. Where we, of course, mean for the prime on the solution to be the kind of derivative that that part of the solution is a function of, right? So x prime is a partial x, it's a derivative with respect to x, and t prime is a derivative with respect to t. So if I plug those in right here, I'm going to put it up here so you guys can see it better, if you don't mind. Then what that gives us here, let's look at it. Ut is xt prime, right? And I've got what, k, and my uxx is what, x prime prime t, right? So I'm just plugging in, the product solution into there. Now what we do is divide by xt. What's that give us? That would give us t prime over t is equal to, I'm going to bring the k to the other side if you guys don't mind. T prime over kt, all right, equals to x prime prime over x. And at this point, I regret using k for that. Is it too late for me to, I mean, it's not the worst thing. I've used a big K in the notes for something that's logically different from that little k. Tell you what, let us just make a command decision here. Let's change that k to an alpha so that there's no danger for confusion, if that's okay with you guys. I hope it's not too late. I'm going to change this k to an alpha. 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 All right. All right, so at this point, we come to a step in the analysis, which is always weird the first time you see it. But the step is this. So I'm going to see if you guys can figure it out. On the left-hand side, we have function of time. Right? On the right-hand side, we have a function of x. What does this say about these ratios? What's the only kind of function which is common to both functions of x and functions of time? Displacement? Physical answer. No, I'm looking for something more mathematical here. Like if it's a function of t and it's a function of x alone, that just leaves you with a constant. The only thing which is both a function of x and a function of t is just a constant. So we can justly say that this is equal to, I'm going to put a minus k here in order to match my notes. All right? See, because what does it mean to be a function of x, right? That means that if we take partial t of x prime prime over x, what should it be equal to? If it's just a function of x, can it have a non-trivial t dependence? Certainly not, right? What we mean by just a function of x is that the t derivative of it's 0. And likewise, just a function of t means that the x derivative of it, of the other side, is equal to 0, right? So if you have both of these partial derivatives equal to 0, that forces those ratios to just be an ordinary Gordon variety. What's even that? Garden variety. Golly. Constant. Okay. Right? So, for this reason, we need to understand how to solve boundary value problems, right? Because as we study the problem of the heat equation, yeah, we see that proposing a product solution brings us straight away to the problem of solving constant coefficient differential equations, right? But what's the this is new and weird, because like let's look at what we're up against. What are we up against here? Like take this thing I just wrote, right? Focus just on this piece here for now. We're going to focus on this piece because this piece we have the boundary conditions for, right? So we need to solve x prime prime plus kx equals to 0, right? Subject boundary conditions. Do you see why we need to do that? If we're going to piece together a solution to the wave equation, see, because that's what we came to. I'm just rewriting that as a homogeneous second order differential equation because, hey, that's our happy place, right? So, although it may be slightly unhappy when you realize we haven't done this before, but it's not too bad. We have all the necessary technology. Let's begin case number 1. Assume the issue x of 0 is equal to 0 and x of L is equal to 0. L here is a positive constant. We might as well work it out for an arbitrary L while we're at it, right? Okay. So here, there are 3 different cases to consider for k. K is a constant. It could either be what? It's a real constant, by the way. Okay? So it could either be 0 or positive or negative, right? Them's your choices. So we'll start with the 0. Let's start with 0. If k is equal to 0, then we've got x prime prime, right, equals to 0, which tells me that x of x is just like, c1x plus c2. And then x of 0 is c2, which is 0, and x of L is then C1L equals to 0. Therefore x is equal to 0. So apparently the k equals 0 case, nothing to see here, right? Nothing to see here. Next, I will look at the k equals to minus beta squared case. So here, this is less than 0. I'm assuming that beta is positive, okay? That's just a convenient way for us to formulate the problem in the context that the constant is negative. It's most convenient to write it that way because then you see we're up against x prime prime minus beta squared, x equals to 0. But I warned you guys about this earlier in the course. We can use Cauchy and Cinch for a problem like this. And as such, this implies that x of x is like C1 Cauchy beta x plus C2 Cinch beta x. Now, if you don't know about Cauchy and Cinch, well, then this devolves into a discussion about exponentials, which you could do and still get through the math, but it would take a whole extra minute. So, great. X of 0 is what? And x of L is what? Cinch of 0 is 0, right? Cauchy of 0 is 1. So I get x of 0 is C1 is equal to 0. Yay. Then I get C2 hyperbolic sine of beta times L is equal to 0. The C1 term's gone, of course, because we already found C1 was 0, so we don't need to think about Cauchy of beta L. That's gone. Fun fact, Cinch is everywhere increasing because its derivative is Cauchy, and Cauchy is at its smallest 1. That means Cinch is always increasing at a rate of 1 or higher. And so it's a strictly increasing function. Cinch of 0 is 0. That's the only time Cinch is 0. So when I've got C2 times Cinch of beta L equals to 0, that forces C2 to be 0. Because I already know that beta L is not equal to 0 because we assume beta is non-zero here. And L is assumed to be non-zero. And as such, this forces C2 to be 0. Looks like x is 0 again. All right, starting to wonder, is there anything to find anywhere here, right? So one last case, k equals to beta squared, positive, right? Again, I'm assuming that beta is positive for our convenience. So x prime prime plus kx becomes x prime prime plus beta squared x equals to 0. We've been down this path before. We know the solution to this. It is what? X of x equal to C1 cosine beta x plus C2 sine beta x. Man, I sure hope this gives us a non-zero solution. Otherwise, we're really up a creek, you know? Like, what are we going to do? We're out of solutions to look for. I mean, we'd have to go back and complain. You know, we have to shake our fist at Fourier and say, hey, how dare you waste our time with this? But don't worry. Well, first of all, you'd have to dig them up. But, you know, don't worry, it's going to work out. We'll see. So, sorry, morbid comments aside. I mean, it's been a couple hundred years. I think it's probably okay. X of 0, besides he's French, x of 0 is, that's right, I said it. C1 is equal to 0, apparently, because cosine of 0 is 1 and sine of 0 is 0, right? But on the other hand, x of the L is C2 sine of beta L. That has to be equal to 0. Now there's hope in as much as we understand trigonometry. How can sine of beta L be 0? We don't, if C2 is 0, everything's over again, right? We want C2 to be non-zero. It must be that the sine of beta L is 0. What does that say? What are the solutions? Beta L equals to what? By the way, oh no. We could be here all day, right?
Yeah, except for pi. So wouldn't it just be beta L is equal to pi? Or no, pi t?
Hmm. 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 I mean, we do know that beta is positive, right? And we also are assuming L is positive. How about this? Any multiple of pi. Zero won't do, because that would force beta to be 0. We can't have that, right? But any positive integer will do. And so you see, we find something a little bit weird here, actually, yeah? Beta actually is equal to n pi over L. Oh man, this is very, look at this. What we just found is that x prime prime plus kx equals to 0 with x of 0 equals to x of L equals to 0 only has non-trivial solutions if what? K is equal to what? Notice this case here, we were working with k equals beta squared, right? We just found the boundary conditions force beta is n pi over L. So in fact, k has to be n squared pi squared over L squared. I mean, this is bizarre relative to what we've done up to this point in the semester. I mean, we solve a differential equation. We think nothing of, does it have solutions or not, right? Of course it has solutions, because we've always been working with initial value problems up to this point. And initial value problems have solutions because the existence and uniqueness theorems for initial value problems are very forgiving. They say if you give me initial data and you give me a differential equation, as long as we're at an ordinary point, there's a unique solution with respect to that initial data set. Boundary values, no such luck. You actually have to have a particular type of differential equation to match the boundary values in order to actually get solutions. That's wild. But that's the way it is. So what we find is that as we go looking to solve these, some of them have solutions, but only for a very particular choice of k. But the cool thing is we found not just one solution, but in fact a whole countable family of them, right? So in fact, what we just found was that x sub n of x has the form apparently, sine of beta was what? N pi x over L, right? Basically, like any one of these guys, you could put a constant in front, right? Like, I don't know, what do you want to call it? B sub n, whatever. Anything here, that solves the boundary conditions, right? As long as we have k is equal to n squared pi squared over L squared, yeah? And it's easy enough to see that that works. Now, if we do this, what happens to the time? See, we've been focused, right, on how to solve the spatial part of the separation of variables problem. Now that we've solved the spatial part, we can go back to the temporal part and we can solve that, right? I mean, let's do it. So if I can erase some of this stuff over here. Ooh, poor choice on my part. I don't know why I erased that. I don't want to erase some things. I don't want to erase here, like, don't just dab. All right, hopefully it won't melt. We'll see. I'm going to keep. I'll keep. we're working on this set of boundary conditions right now, right? So we'll keep these for reference. Okay, so looks like we have, we're up against t prime equals to minus k alpha t, right? But we have learned that the k is actually what? If we want to have non-trivial solutions for the spatial part, we don't have much freedom in the matter. Oh yeah, what you said it. You said it. What was it? N squared pi squared over L squared. Okay, so we've got minus n squared pi squared. There's that alpha there over L squared t. Can we solve this equation? Let me demystify it for you.
It's t prime plus and that thing equals to 0.
Right. Well, I mean, what's the characteristic equation here? Lambda equals to what? I mean, this is a constant coefficient ordinary differential equation first order, right? So write down the characteristic equation here is simply lambda from t prime, and over here, minus n squared pi squared alpha over L squared, you know? So apparently my solution for t is just the exponential of, you know, minus n squared pi squared alpha divided by L squared, bless you, times t. There you go. Woohoo! There's my temporal solution. We can do it for each n, right? Now we can put them together. So now here, this is Fourier's mad step. He said, okay, so write the general solution like this. You take the sum, n equals 1 to infinity of b sub n sine of n pi x over L e to the minus n squared pi squared alpha over L squared times t. And this right here is a, you know, the general, let's say, formal solution to the heat equation. That's as far as we can go with the data which I've so far given you. Now let's think about this logically. I've told you you're looking at this like rod, right? And we've got the temperature is 0 here, and we got the temperature is 0 over here, right? But if you want to tell the story of what the temperature is on like this metal rod for time positive, what do you need to know as a starting point? Like, doesn't it matter how the rod starts out? Like, is it hot to start with? Is it chilled? Is it hot in the middle, but cold on the end? Like, what's the deal to start with, right? We need to know, you need the initial temperature distribution, right? You need to know what is u of x comma 0, right? We need to know that initial temperature profile. So if that's given, if we know that u of x comma 0 is equal to, let's say, f of x, right? Suppose that this is the given initial temperature. Then what does that mean about this general formal solution? Like, what happens when you plug time equal to 0 into your general formal solution? Something pretty nice happens, right? It's just that. The exponentials go, e to the 0 is 1, right? So now to solve the problem, we simply need to find what are the B sub n's, right? Solving this initial, solving this heat equation problem then has been reduced now to the problem of figuring out what the B sub n's are. How do you think we should do that? I mean, this is the thing that was so offensive to mathematicians, at least some, when Fourier first suggested it, because he was saying that you could build any initial temperature distribution from just a sum of sines. Why should that be? Can every function be attained by just taking a sum of sine functions? Like, is that mathematically reasonable? Is that really something you can do in this context? I mean, I hope so, because if we can't solve the heat equation with this method. So let me put it up here. We're trying to solve u of x comma 0, which is equal to f of x, equals to the sum, n equals 1 to infinity of b sub n sine of n pi x over L. We need to solve that. There is a rather nefarious trick that comes into play here, which is integration. So what we do is something like multiply by, I don't know, I think it's the integral from, oh, come on. So if I do something like integrate from 0 to L of f of x times the sine of, let's say, p pi x over L dx. Well, then that's going to be the sum n equals 1 to infinity b sub n times the integral from 0 to L of sine of n pi x over L times the sine of p pi x over L dx. Now I made a rather ginormous step there. I pulled the integration inside the summation. Now, remember, sine theta sine beta is minus 1/4 e to the I theta plus e to the minus I theta. If I could just remember the identity, it'd be lovely, but I don't. So I have to work it out. You'll forgive me. These are minuses. I'm a dummy. So if I haven't made some silly mistake, this is the sum n equals 1 to infinity of b sub n integral from 0 to L of 1/2 cosine of n minus p pi x over L minus the cosine of n plus p pi x over L dx. And in a nutshell, This is 0 unless n is equal to p. In which case, if n is equal to p, what happens? This integrates to 0, and we're just left with L over 2. So basically this works out to, as you work it out, B sub P times L divided by 2. And so we find the formula B sub P is actually equal to 2 divided by L times the integral from 0 to L of your given initial temperature distribution times the sine of P pi x over L dx. This formula right here is part of the theory of Fourier analysis. That's the formula for the sine series, the coefficient. So you see, all we have to do is take the integral of the given initial temperature distribution, multiply it against the sine like that, and that will tell me the value I need to put next to the sine to build the initial temperature distribution as a sum of sines. So.
What is P exactly? Like, sorry, I'm just not gotten that.
Oh, so listen, like the whole problem here is we're trying to solve, like our goal here is to solve for Bn. And so the idea is a lot like, you know, you've got a vector, which is v1, vn. I'm trying to solve for vj.
Yeah.
So I know that vj is actually like v dot x hat sub j, let's say,
Yeah.
in my notation. And this is the analog of that.
Okay.
If we multiply both sides by sine of px, and then we integrate from 0 to L, that's like taking a dot product in function space. Because of the integration working out as it does, the integration works out so that it's 0, except in the case that you're in the pth component.
Okay.
I mean, there's a Kronecker n comma p here, I suppose, but
Yeah.
I feel like there's this, well, anyway, this is, it's a case-wise calculation. But that's Fourier's trick.
Okay.
That's not a small step. That's like a genius step, right? Like I'm showing it. I don't know if I'd ever thought of this, but after I saw it, I was like, oh, very sneaky. And so we'll do this again and again and again. This is the heart of what makes Fourier analysis work. It's multiply by sine or cosine and integrate. And it turns out that sine and cosine are like orthogonal with respect to this notion of inner product. Anyway, more next time. Thanks, guys.